The 1B, as I mentioned just now, is already on Moodle. If not, I hope you have received it via my email. Okay, if you have it, refer to it. I'm not sure whether it's so fresh and so new that I'm not sure if I have it on my. Just a moment. You see? Okay, right. Let's see, Okay. I call it 1B because it's still on crankshaft journal bearing. And actually, it is quite similar to 1A, which we have done before. Because we just completed 2, right? So back, you know? So then back. On the crankshaft, we call it 1A and we call it 1B. Okay? Because for 2 crankshafts. Okay, next year, I will renumber it properly. This last, just insert. Not from me, but it's from the fluid mechanics lecturer in Glasgow. Okay, the crankshaft bearing of an automobile engine is lubricated by oil with a dynamic viscosity of 9.6. This 9.6. And look, remember the units, be careful with units. Okay. 10 to the power minus 3 Newton second per meter square. That's it. And the density 920 kilogram per meter cube. So the diameter of the bearing is 0.0762 and its clearance is 3.175. Okay. So that's the clearance. The shaft is 3.175 times 10 to the minus 2 meter long. So it's a very long shaft. And it rotates at 3,600 RPM. So the oil flow in the bearing may be modeled approximately as the flow between 2 parallel plates. This as usual, right? Just like the Earth is round. But because we consider just a small part of it, so we see this as flat, right? Flat plate, when upper plate moves and the lower plate remains fixed. The Navier-Stokes equation of motion of the oil flow with suitable assumptions may be expressed as this. If we are given this expression, second order partial differential of d square u, you're going to display dy squared, this is 1 over mu, del e del x. Okay? And this is what we are familiar with. Okay? U component, z component, and this plate is moving. Okay? This is actually the engine shaft for this part here. So there is the moving part, moving plate. Okay? This is the fixed plate. So moving plate, 6-1. Right? So first is, by applying appropriate boundary conditions, derive the following expression for the velocity component u of the oil flow. And okay, u of the oil flow, okay, derive the following expression. So derive this expression for u. Next, taking zero pressure gradient. Okay. Next, taking pressure gradient as 0, calculate the shear stress acting on the shaft. Shear stress means calculate tau. Next, determine engine torque on the shaft caused by the shear stress, the torque, engine torque. Then we did engine torque also before Chinese New Year. Okay. From the top, determine engine power dissipated in the bearing. I hope you can still remember the expression relating power and torque. Huh? Power for circular motion here of a shaft. What is power? Power is the torque times the for shaft and rotating power. Power is equal to the torque times the omega. Okay, angular velocity. Got that, huh? And finally, determine the Reynolds number. Okay, determine the Reynolds number. Okay. Okay, let's do one thing at a time. Okay, one, eh? One. So we are given, so we have to, in fact, this one I will not do all, I will do all this similar to 1A. Okay, so when you look at 1A, if you look at 1A, you will get the same expression, I think, if you recall. So there's no need for me to work through it. Let's look at 1A solution. They go to the same steps. And in fact, you find that it is the same expression as U for 1A. So that I will not do. You just follow what is done to the first example. Okay, the same steps. Alright? Done. Done, eh? See example. Instead of 1, I call it 1A now. Okay? See example 1A. The same steps are not what going through. Okay? And the same expression. Okay? 2. Determine engine torque on the shaft caused by the shear stress. Okay, determine engine torque on the shaft caused by the jump went too fast. 2. Taking the zero pressure gradient to calculate the amount of shear stress acting on the shaft. Okay, so given, what are we given here? Zero pressure gradient, del V del X equal to 0. Okay, so what's the expression for shear stress? It's equal to mu del U del Y, which is what? How can we make it more familiar? Del U, what's del U del Y? What's del U del Y? From the first part, you got U already, right? You got U. So you differentiate. Differentiate what you got in part 1. Expression for U, del U del Y, you will get what? U, it's U, it's U, U over here. Okay? Now, so, where do we go from there? Because eventually the question says, calculate the amount. Calculate the amount means it has got a number. Calculate the amount. It's good. It's simply leave it as expression, you know. You leave expression, what's the amount? What's the number? No number. So you only get maybe half the mark only. So understand question very carefully. Determine the relation. End of expression. Calculate the amount, not calculate. So let's say I have a value at the end. Okay, or else if you have expression answer, you get half the marks again. So then, what numbers can we put in? We are given U. Are we given A? Yeah. Are we given A? Yeah. A is 175 minus 5 meters. So what is U? What is u then? We know mu is numbers, we know a is number. What is u? Anybody? Put in some number for u. 1. Maybe 0 better. Answer is 0. 1 also 0. Okay, remember, when we talk about circular motion, think of all the possible expressions involving velocity. Okay? So, remember, when something is rotating, it has an angular velocity. Okay? It also has a linear velocity. So, u is actually the linear velocity. We take u here to the linear velocity. Okay? But are we given the angular velocity here? Yeah, it rotates at 3,600 rpm. So from there we can get our omega. How to relate omega to u? U is equal to omega r. Remember, u linear velocity is equal to omega r. Okay, right. I use capital omega. Omega is u over r, or u is equal to v omega. Right. Okay, in other words, i.e., u is equal to omega r. What's our omega? How to convert rpm to omega?
Therefore.
And be careful of the units, this is rpm. So what's the omega? If you are given n rpm, how is it if, and your omega is in radians per second? How do we convert this to radians per second? Given n rpm, how do you convert to radians per second? Anybody? Open here. Okay. Alright. Yeah, for those who are not very sure, is 2 pi n over what? Over 60 divided by 60 seconds, or divided by 1 minute divided by 60 seconds. Okay, so n rpm is equal to 2 pi n over 60 radians per second. So remove the question mark now. Okay, so omega is equal to 2 pi n is 3600 over 60, and don't forget r becomes what? R becomes 0. Everything 0 again, no? Also 0 marks again for you. 2 zeros there. So R will become a A. Okay? R will become A because it is at the peripheral, of the shaft. At the peripheral of shaft, that's the V. Shaft rotating. So that is the omega. Where's your V? V is actually your U. So in this case here, this is your. You are given the diameter, so we can get the R. Half of it is what? Be 0.0381. Okay. 0.0381. 1 there. Okay. Alright, so you get a number. And okay, I just simply make it short. So tau therefore is equal to 14.336. Make it here better. Okay, so therefore tau. To substitute, you get 4342.9 Newton per meter squared. Okay, we cut it short. Alright? If we substitute back to your expression for tau, and you get tau, the shear stress is equals 4342.9 Newton per meter squared. Okay, 3, yeah? 3 says, determine engine torque. Okay, what is torque? Torque T is of course force times the radius. Okay, there's an expression for torque. Okay. So, what is this force? What is this force? Force is actually the shear stress times the surface area. Shear stress times the surface area. So is shear stress times the surface area. Surface area is 2 pi r times the L. Okay, 2 pi r times L. And then times r. Okay. And what is L? L is the length of the shaft. The length of the shaft. Okay. The shaft is just going reciprocating. So the length is the shaft length. Okay. L is shaft length. Okay. So in this case, all the values known. You have a tau already. Now, tau above 4342. And you have got your. So in this case, again, is at the surface of the shaft. So R becomes A. So R becomes A. Okay. So in this case, so R becomes A. So you have 2 times pi times the others, if you put it all correct, it is 0.03175 times R squared, which is actually your A squared, 0.0381 squared to A squared, times your stress is 4342.9. Okay? And you get the answer as 1.258 Newton meter. 1.258 Newton meter. And next, finally, the sweep of 4 and 5. Okay. You got the top, now get the power. So you got the top, now get the power. So what is the power? Case. Power, as I mentioned earlier, for relating power, W is work done. W is work done. Okay? So you put a dot there, it is work done divided by time. It becomes power. Okay? Put a dot above W is work done per unit time. It's power. So W dot is power. And the formula relating power and torque for a circular shaft is simply torque applied times the omega. Okay? Times omega. Okay? And you know what is omega? Is torque times U is U over R. And R is A, because of on the shaft surface. So just torque is 1.258 times U. We got U 14.36 over A is 0.0381. So we get about 474 watts. Okay, 474 watts. That's the power dissipated by the shaft. Then finally, Reynolds number. Reynolds number easy, Reynolds number is again rho Okay? And with that, you'll be able to get, plug in all the numbers, try all the numbers, you get 43.7. Okay? So this is very much less than 1500 or 2000 for transition. So laminar flow. Laminar. Okay? So that's very quickly the 1B. Done. So far so good. We go through two exercises really. Okay, right. Okay. Any questions? Right, no questions. Good. All clear, huh? Right, next we go on to the next topic on the Bernoulli principle. Bernoulli principle.